Good morning, afternoon, or evening. How y'all doing today? Welcome back to Mr. Moore's Honest Geometry class. We're continuing with circles. Yes, circles is a very long chapter. There's a lot entailed with circles. Please, I do suggest strongly that you start reviewing everything we've learned from chapter 10 so far. We have 10.7, 10.8, and 10.9, so it's a very long chapter. A lot of information. Luckily, it all correlates together, and it makes sense, and it builds upon itself. But I strongly suggest that this weekend, you start studying from 10.1. What does that mean? Redo some homeworks. Look at the quizzes. Go over the theorems. Rewatch the videos. Because next week, we will have a test on this, and it's a major test. So let's continue, guys. Today, we're talking about inscribed and circumscribed polygons. And an inscribed polygon is this guy here in blue, hence inscribed. We all know what a polygon is. We've already talked about polygons. Okay, it's a figure made up of 3 or more segments. And an inscribed polygon is a polygon that is literally inside of another figure. In this particular case, it's inside of a circle. Okay, it is inscribed if and only if all vertices intersect the circle at one point. And as you can see, these blue points are the intersection points of that polygon on the actual circle. So that makes it inscribed. Circumscribed, here in red. Circumscribed polygons occur when a polygon is actually drawn around a circle, or it's the inverse. It's when a circle is inside of a polygon. Okay, all sides intersect the circle at one point, though, once again. But this polygon is circumscribed about the circle because at every intersection point, it's hitting the circle. Yes, sir. That's a very good question. Would the circle be inscribed inside of the polygon? Yes, that's pretty much what I said. Thank you. Okay. When you have a polygon inscribed inside of a circle, you have what's called an incenter. When you have a polygon circumscribed about a circle, you have what's called a circumcenter. Okay? Now, the inscribed polygon theorem. The inscribed quadrilateral theorem. Inscribed quadrilateral theorem. If a quadrilateral is inscribed inside of a circle, it should be of A, I apologize, then its opposite sides are supplementary. So this should be inside of a circle. Then its opposite sides are supplementary. So what does that mean? Since I have this polygon inscribed inside of a circle, angle A plus angle B will equal 180. Hence, angle A and C are supplementary. Angle B and angle D, the sum of those two are 180. Therefore, angle B and D are supplementary. Yes, sir. Come again? Yeah, opposite angles. Opposite angles are supplementary. I apologize, not sides. Thank you. Good catch, sir. Thank you for that very much. And again, I apologize. No excuses. Thank you. So opposite angles of an inscribed quadrilateral are supplementary. It only works for a quadrilateral, not any polygon, but solely for a quadrilateral. Pretty easy, right? So far? Hello? Yes? No? Maybe? Kind of? Sort of? Okay. Inscribed parallelogram theorem. This is a very good one. If a parallelogram is inscribed inside of a circle, then it must be, believe it or not, a rectangle. A must be a rectangle. Why? Let's think about this for a second. Okay? First of all, thank you. The quadrilateral, this parallelogram is a quadrilateral. Opposite sides are going to be equal, of course. However, let's look at the diameters here. BD and AC are diameters. Okay? Aren't the diameters of a circle congruent?
Yeah.
Okay. If we're looking at the quadrilateral there, the parallelogram, quote unquote, if the diameters are congruent, doesn't that mean that now AC is congruent to BD? So doesn't that really mean that the diagonals are also congruent? Guys? Yes? Aren't the diagonals of a rectangle congruent? Okay, very good. In this particular circle, let's call it circle O, okay, always in the center. So therefore, OA is congruent to OC, which is congruent to OB, and which is congruent to OD. They're all radii, so they have to be congruent. Don't the diagonals of a parallelogram, don't they bisect each other? Yes, very good. So therefore, this must be a rectangle. Now, I know what some of you are thinking already. Isn't that a square? Well, think about it, guys. A square is also a rectangle. But it's not necessarily going to be a square always, but it will always be a rectangle. Was that the question you were going to ask? Thank you. I thought so. Okay. Now, in order for this to be true, though, the parallelogram must be inscribed. If you look at this guy over here, you have a parallelogram in there. But is that truly inscribed in the circle? No, because you just have two intersection points. What about these guys? They don't intersect. So therefore, that is not inscribed. Okay? That is a parallelogram that is inside of a circle, sure. But it is not categorized as being inscribed in a circle. Okay? Does that make sense here, guys? You with me? So again, the reason it's a rectangle is because the diagonals are congruent and the diagonals do bisect each other. Okay? Does that make sense? So again, this is technically a square as well. But it's not always going to be a square. Why is it not always going to be a square? Because you can have different chord lengths. All chords are not congruent. If the chords happen to be congruent, then yes, that's a square. But then it goes back to being a rectangle. Because a square is a rectangle, but a rectangle is not necessarily a square. Yes, sir? Correct. If the diameters bisect each other, it's always a square. Yes. Does that make sense? Okay. So, example number 1. You have a parallelogram ABCD, which is inscribed in a circle. Okay? And its diagonals intersect at a point called E. We want you to draw the figure. Well, let's draw a figure. Go ahead and draw a circle and draw a quote-unquote parallelogram inside of it. But when you draw a parallelogram inside of a circle, it has to be a rectangle. Okay? Now, does that look like a rectangle? No, it doesn't. But it is. It's a rectangle. Okay? You with me here? So far, guys? Hello? Yes? No? Maybe kind of, sort of? Okay. Let's look at C first. What is true about this parallelogram ABCD? Using what we just learned, what is true about it? It must be a, very good. Okay? This must be a rectangle. Not too difficult, guys. Let's look at B now. What is BD? What is BD? Okay. It is a diagonal of the rectangle, but what is BD since this rectangle is inscribed inside of a circle? BD is a diameter. And what is the degree measure of a diameter? 180. You with me here, guys? Okay, now, if AB equals 5 and BC equals 6, I want you to find AC. Well, let's think about this. If BD is a diameter, isn't AC also a diameter? What did we learn about inscribed angles inside of a semicircle? They are right angles. Very good. Because remember, it's half of the arc. The arc is 180. So in this particular case, since I am defining for you that AB is BC, in this particular case, is this a square? Guys, is this a square? No. It is a rectangle. So again, if I define that the chords making this parallelogram are congruent, which they're not going to be because a parallelogram don't have all equal sides, it is a rectangle, okay? So what would AC be? How do we find this? Pythagorean theorem. So AC squared equals AB, which is 5 squared, plus BC, which is 6 squared. So AC squared equals 25 plus 36. So AC squared equals 61. Square root of AC. AC equals square root of 61. And you're done. So I really need you to understand the whole parallelogram being a rectangle. You have to remember the rules of parallelograms. Parallelograms, the diagonals bisect each other, correct? But in a parallelogram, are the parallelogram diagonals congruent? No, they're not. But a rectangle's diagonals are congruent, correct? All right. Are all sides equal in a parallelogram? No, opposite sides are equal. Opposite sides are also parallel. So those criteria give you the rectangle, not the square. Okay, I need you to understand that. Does that make sense? It's pretty simple, right? Yes, sir. Yes, sir. Alrighty. Now, let's see how this works in a proof. Quadrilateral ABCD is given, and it is inscribed inside of circle O, as you can see in the figure to the right. They want to prove that angle B is congruent to angle ADE. So as always, I have my figure down here, guys, so we can relate to it. And of course, one is quadrilateral ABCD is inscribed in circle O. Okay, what's my next one? Very good. If we use the inscribed quadrilateral theorem, angle B, okay, this guy, is supplementary to AD, actually, ADC. That should be a C. That should be ADC. Sorry. Oh, a lot of mistakes today. My bad. That's my bad. Okay? So they're not congruent, but they are supplementary. Why? Because of the inscribed quadrilateral theorem. Then, where can we go from there? ADC is supplementary to ADE, absolutely, because definition of supplementary lines. And then I want to prove that angle B is congruent to angle ADE. Supplements of the same angle are congruent. Since angle B is supplementary to angle D, or angle ADC, and angle ADE is also supplementary to ADC. That means that angle B and angle ADE is supplementary to the same ADC. Therefore, they are both congruent. Easy peasy. Yes, sir. This quadrilateral does not have to be a rectangle. It had to be a rectangle if I had defined for you that it was a parallelogram. If I said parallelogram ABCD is inscribed inside of a circle, then it would have to be a rectangle. But all I said was quadrilateral ABCD, bless you, was inscribed. So if it's a quadrilateral, the properties that are activated is that the opposite angles are supplementary. Does that make sense, son? Thank you very much. Told you it'd be a nice and easy lesson. Thank you. Hope you learned a lot and have a great day.